just to make sure that everything is in order. If you can hear my voice and if you can see my screen, please type yes in the chat box. Okay, all right, so thank you very much. So another thing is to make sure that this is where we stopped last time. I think we have discussed the time response of a second order system. So now I think the last thing that we discussed the last time is this example 4, if I'm not mistaken. So today we are going to, yeah, I guess this is where we stopped last time. So today we are going to look at the steady state error. Before we move on, let me clarify a few things. See, our test 1 is schedule. See, somebody say schedule. Somebody pronounced that as schedule. So I say it's schedule. So our test 1 is schedule on November 21st, this Saturday. So if there is no further information, we need to assume that that is the official date for our first test. Okay, so 21st of November. But most likely, because we have 9 sections, I can't promise anything. So we have to coordinate with other sections. Probably some of the section is behind. So we'll wait and see. But for the moment, let us just assume that the test is going to be this Saturday, and we are right on schedules on schedule. So the test is going to be covered up to time response of first order system. So if you have submitted your first assignment and before you go into your first test, you should at least finish question 1 of assignment 2. So that is where first test is going to cover up to question 1 of assignment 2. The time response of second order system will not be included in the test. So you can see that we are ahead of schedule. So as long as you finish first question of your second assignment, we should be all right. So just be ready. I will make further announcement in our chat group. Okay, so that is out of the way. So far, when we evaluate the performance of the control system, so far we just look at the transient part of the response. The transient part, meaning how fast the system is going to respond. Is there any overshoot? How fast is the system going to settle? And is there any oscillation? The frequency of oscillation. Those characteristics, those quantities are properties of the transient part of the response. We can also evaluate the performance of a control system by looking at the steady state part of the response. Namely, we are going to look at the steady state error. So today we are going to talk about how can we evaluate the steady state error of a system. So by constructing a feedback control system, we are invariably going to induce a steady state error, as we have seen in a few examples so far. So today we are going to learn how can we evaluate the steady state error. Most of the time, what we actually want is zero steady state error. What's going on here? So if you look at this closed loop system, so the error signal here, E here, we want to be equal to 0 eventually, but sometimes we cannot get error signal to be 0 even in the steady state. So how can we evaluate this error signal E? So E here represents the error signal, which is the input minus the whatever output multiplied by the feedback loop transfer function. So from this diagram, we can now solve for this error signal E. It is quite simple. You can see that E is just equal to the input signal minus y multiplied by h of s, the first equation here. But y itself is E multiplied by g. So you just substitute y here is g multiplied by E, bring everything to the left-hand side, and you can solve for E, just equal to 1 divided by 1 plus gh multiplied by u of s. So this is the expression for error signal in terms of Laplace variable E of s. So this is the expression of error signal in Laplace transformation. You can see here, error depends on the input, u h of s, u of s, and then the open loop transfer function gh. But this is in Laplace domain. We want to evaluate the error signal in time domain. So how can we evaluate the error in time domain? That is called the final value theorem that we can use to evaluate the error signal in time domain. So it is called the final value theorem. So the value of a function e of t when t approaches infinity, this is in time domain, is equal to the limit of s approach 0 as multiplied by e of s in Laplace domain. So this is just a theorem. So we can evaluate the steady state error in time domain just by using this steady state final value theorem. Let's go to my notes. I have derived some notes here. So this is the expression. The first equation here, E of s is equal to 1 divided by 1 plus gh of s u of s. So this is the expression for error signal in Laplace domain. So we want to evaluate the steady state error in time domain. ESS here stands for steady state error, which is by definition we want to know the value of the error in time domain when t approach infinity. See? So this is a steady state. We let time goes to infinity, then we evaluate the value of the error in time domain. So using the final value theorem, so that is just the limit as approach 0 as approach 0 as multiplied by capital E of s. This is in Laplace domain. So and then we can now substitute E of s by this expression. Just substitute in this definition, and then we get this. This is now the steady state error in time domain. So you take the limit as approach 0 and evaluate this expression, and then you will get the steady state error in time domain. You can see here the steady state error is a function of two quantities. One is the input signal. So the steady state error depends on input u of s. For different input, you're going to have different types of error. It also depends on gh of s, which is the open loop transfer function. It depends on the class or type of the system. So steady state error depends on two things. So now we are going to look at a different type of input. One of the factors that will determine steady state error is the input, which intuitively we know that already, that if you give different input signal will generate a different steady state error. So now we are going to look at three types of input. Okay, so for unit step input, u of s is just one of 1 of s. So for ramp input, which is u of t is equal to t. So this is when you take the Laplace transformation, you have 1 over s squared. For parabolic input, and then u of s is 1 over s cubed. So you see, this is u of s has take a different function when the system is subjected to different type of input. And then we need to evaluate for each one of the input. All you have to do is substitute u of s inside this expression for steady state error, and you go ahead and evaluate as approaching 0. So here, let's take a look at the unit step input. U of s is equal to 1 over s. You put 1 over s here. There's s on top of it, so you can cancel. So 1 of s multiplied by 1 over s is going to go away. So you get 1 plus g hash of s. So basically, when the input is unit step, and then this is your steady state error. For simplicity, we can replace that Kp is equal to limit as approach 0 of g hash of s. We name that what is that? What's the name? Okay. I suddenly forgot. V for velocity, displacement. So this is called the displacement error constant. And you need to repeat that for ramp input, and you need to repeat that for parabolic input. Again, for a ramp input, u of s is 1 over s squared. Just substitute that into the steady state error expression, and then you have s multiplied by 1 over s squared. Of course, you're going to have 1s at the bottom here. All right, so now when you take the limit s approach 0, so the first term s here is going to go to 0, so that expression is going to simplify to just the limit 1 divided by s multiplied by g h of s. And for simplicity again, okay, we define kv. Kv is known as the velocity error constant. Kp is the displacement error constant. Is it Kp or Kd? What the hell is this? Let me double check. No wonder I was confused. See, for some reason, use Kp. Why don't you just use? Oh, I know why we don't use Kd, because we use Kd for something else. All right, so Kp is known as displacement error constant, Kv is velocity error constant, and Ka is acceleration error constant. So the steady state error will depend on the type of input. If you have identified the input, then you can take any of this expression to evaluate the steady state error. The steady state error also, if you see here, Kp, Kv, and Ka, which is this displacement error constant, velocity error constant, acceleration error constant, is a function of open loop transfer function g h of s. It depends on g h of s. This is where we classify our system, the system type. If the system is type 0, g h of s is going to have a different expression as compared to system type 1 and type 2. For example, here I have listed an example for a system class or type. Okay. Yeah. See, if the system is class 0 or type 0, you have in the numerator of the open loop transfer function, you have s to the power of 0, which is just 1. So this is for class 0. And this is for class 1. You have s 1 divided by s plus. This is an example. For example, just one factor s plus 1. So the single s here is raised to the power of 1, and then you have class 1 or type 1. Class and type we use interchangeably, and this is class 2, s squared multiplied by some factor. So you can see that all this error constant will depend on the expression for g h of s. Okay, so you have three types of input. You have 3 types of class, and you're going to have 3 by 3. There is 9 possible steady expression for steady state error. So to simplify that, we have this very useful table that you can refer. So this is a very convenient table that you can refer to. Okay, so you have 9 steady state error here. First, it depends on input. For different input, you're going to have different types of error, and then you're going to have the class or the system. So you can always come back to this table and pick whatever steady state error that is corresponds to a particular problem. Again, if you don't have this table, and then you can always go back to the definition of steady state error. So we can always come back to this expression. So this is the general expression for steady state error. You can plug in the equation and then you can get the steady state error. So that's how you evaluate the steady state error. So a good system is going to produce 0 steady state error. So here you can see class 1 and class 2 will produce a 0 steady state error for step input. And class 2 is going to produce 0 steady state error for ramp input. For parabolic input, of course, is very difficult to trace parabolic input. So even class 2, you're going to have some value of steady state error. I don't have to ask this question. I know that I feel like I'm talking to myself. Don't worry about it. Let's take an example and then see whether you understand what's going on or not. Okay, let's take a look at example 1. Example 1. Calculate the displacement error constant and steady state error for a system with the following open loop transfer function. So you are given this open loop transfer function GH of S. See, this is not the overall transfer function. This is the open loop transfer function, GH of S. See, so this is the closed loop. This is the closed loop block diagram. G is the forward path transfer function. H is the feedback loop. The overall transfer function is G divided by 1 plus GH. We already know that. But the open loop transfer function is just the loop gain, G multiplied by H. It is known as the open loop transfer function. All right. So in this example, we are given just the open loop transfer function. And then we are asked to calculate the displacement error constant, which is Kp. And then we can now evaluate the steady state error for a different type of input. And you can see here, this is type 0. You can see this is a type 0, system type 0. And if you look at the table, okay, this is type 0. For step input, you're going to have steady state error. For ramp input, you're going to have infinity error. It's infinitely large error. For parabolic input, you're going to have infinitely large steady state error as well. Now we're going to show that using this example. All right, so let's go back to my notes. Okay, there you go. So this is the open loop transfer function, GH of S, which is the forward path transfer function G multiplied by the feedback path transfer function H. It is type 0. We know that it's type 0, but we can evaluate Kp. It's just the limit of S approach 0 GH of S. And then you substitute GH of S and take the limit as H approach 0. So you get the limit as 1/2. So for unit step input, the steady state error is 1 divided by 1 plus Kp. So the steady state error is going to be 0.667. This is for the unit step input. If you go to the table, our system is class 0. So this is for a unit step input. So this is the steady state error. And from the table, the steady state error for ramp input is infinite. The parabolic input is infinite. We can prove this. So this is for unit step input. So this is the steady state error when the input is unit step. If the input is the ramp input, if the input is a parabolic input, from the table, you can see that the steady state error is infinite. So let us show that. So to evaluate the steady state error for ramp input and parabolic input, you need to evaluate the velocity error constant and acceleration error constant. So this is the expression for velocity error constant. This is the definition of acceleration error constant. Substitute the expression GH of S and take the limit as h approaches 0. See, this is 10 multiplied by s now, because this is s multiplied GH of S. So you get kV is equal to 0. Similarly, now you have s squared, so Ka is equal to 0. Now the steady state error is 1 over kV, 1 over Ka, so 1 over 0 is infinite, 1 over 0 is also infinite. Okay, so this is a steady state error for ramp input. This is a steady state error for parabolic input. So this system can only cater for, can only track the step input. So there's a steady state error. Okay. For other than step input, if the input is ramp input or parabolic input, the steady state error is going to be infinite. Okay, now do you have any question now? All right, okay, no question. No question is good. All good, all right, okay. So now let's take a look at the next example. Next example. Find out the error constant for the system shown below. So there is a little mistake that present in this example. So this is not 4 over 3. No, it should be 4 over s. This is k plus 4 over s. This is a PI controller, proportional plus integral. So make a correction there. So there is not 4 over 3. This is 4 over s. So find out the error constant for the system shown below. So for you to be able to find out an error constant, you need to get the open loop transfer function. Open loop transfer function is just g multiplied by h, not the overall transfer function, not the g divided by 1 plus gh. The open loop transfer function is just g multiplied by h. So g is the forward path, h is the feedback transfer function, which is just 1. So once you get the open loop transfer function, then you can evaluate all the error constant. All right, so this is the correction that you need to make. This is 4 over s, not 4 over 3. That's 4 over s. Therefore, you need this open loop transfer function, GH of s. Okay, so this is the loop gain. So k plus 4 over s multiplied by that, and then there is the open loop transfer function. You can simplify k plus 4 over s. It's just ks plus 4 divided by s. So we prefer in the form of ratio, and then multiply by the system transfer function, the system to be the system that we are interested to control, multiply by that. So now we have the finally we have the expression for open loop transfer function. You can clearly see here that this is system class 2 or type 2. So in the denominator here, a single s that you factor out here is raised to the power of 2. So this is the system is 4th order. The highest s in the denominator is 4. So this is a 4th order system, but this is type 2. S raised to the power of 2. This is type of class 2. Okay, so if you go back to the table for type 2 system, so this is class 2, you're going to have 0 steady state error for step input, 0 steady state error for ramp input, and you have some value steady state error for parabolic input. We can go ahead and evaluate the error constant Kp, Kv, and Ka. All right. Once you get the open loop transfer function, it's just a matter of substituting into the correct expression. So that is your Kp infinity. Take limit as s approach 0. So you have 0 in the bottom there. So you get infinite. S multiplied by GS of S is still infinite. But now Ka here, the acceleration error constant, since you multiply by S squared, and then you already have S squared in the denominator, and that will cancel out. So when you take the limit S approach 0, all you have is 4 divided by 16. So this is the acceleration error constant is equal to 0.25. And from there, you can evaluate the steady state error, just substitute in the correct formula. Okay. So if the if the input is unit step, and then you have 0, 1 divided by 1 plus infinity, so you get 0, 1 divided by infinite, then you get 0 again. So 1 divided by 0.25, so you get a steady state error of 4. So now so this is the error for different type of input. And you can see here, system type 2 or class 2. If you go to the table, so this is class 2, steady state error is 0 for unit step, ramp input is 0, and steady state error 1 divided by Ka for parabolic input. So this example illustrates how you calculate the steady state error. So it is purposely chosen system of type 2 to illustrate the steady state error for class 2 type of system. Do you have any question? So now we have another measure that we can evaluate the control system. Instead of just looking at the transient part, which is how fast the system responds, is there any overshoot or not, how fast the system settle down. The effectiveness of a control system can also be measured using the steady state part of the response. In this case, we look at the steady state error. Okay. Do you have any question? All right. Okay. So next, we are going to discuss the control action. If you only want to follow 1 hour of my class, let's say you just you are a smart Alex. Okay, I just want to enter 1 hour of my class. Then this is where I suggest that you should follow my class. So this is the summation of what we are going to do. Doctor, even though we know that it is class 2, do we need to show Kp and Kv? No. Okay. It depends on the question. If the question asks you to compute Kp and Kv, then of course you need to calculate Kp and Kv. So in this example, so we cover everything. So we cover all possibility, all type of input. So in fact, it depends on the question. Normally we are just going to look at one type of input. And given one input, whether unit step or unit ramp or whatever, you just need one of the error constant only. But this is just to illustrate the usage of those error constant. So it will depend on the question. Okay, it just depends on the question. Okay, I don't want to continue with this control action yet. So let's take a break and then come back at 4:45, and then we will continue discuss this control action. Okay, so let's take a break. Let's take a short break and then come back at 4:45.